Let's start. Yeah, it's a start. It's recording now. You can start now.
Okay. So the first topic, microprocessors and microcontrollers. A microcontroller is an integrated circuit that performs a specific operation in an embedded system. A microprocessor usually consists of a processor, memory, input-output peripherals on a single chip. Now we'll look at the microprocessor. A microprocessor is a controlling unit of a microcontroller. What a microprocessor does it takes input instructions from the memory, it decodes it, processes it, and produces an output. Microprocessor performs early operations and it communicates with other devices connected to it. So now the differences between the microprocessor and a microcontroller. The first difference is in a microprocessor, the peripherals are connected externally. Like a microprocessor just consists of a CPU. All the other stuff, ROM, RAM, input-output ports are connected externally to it. While in a microcontroller, this whole thing, like the CPU, RAM, ROM, serial interface, input-output ports, this whole thing is a microcontroller. That is, the peripherals are inbuilt. Another point of difference is a microprocessor is not made for a specific task. A microprocessor does complex stuff, like for example, a personal computer. It depends on the user. A user can play games, a user can do web browsing or watch videos or photos. A microprocessor is not made for just one task. While in case of a microcontroller, it already has a predefined work. For example, cameras or washing machines. They already they are made for one specific task, right? So these are the main differences between microprocessor and microcontroller. Some other differences are difference in cost. The microprocessor does complex tasks and it is meant for heavy processing. That's why the cost of microprocessor will be more than a microcontroller. In case of power consumption, the power consumption of microprocessor is greater than a microcontroller because the components are connected to it externally. Even the clock speed of a microprocessor is greater. A clock speed means the processing power or processing speed. So the processing speed or the clock speed of a microprocessor is 1 gigahertz to 4 gigahertz, while that of a microcontroller is 1 megahertz to 200 megahertz. I'm sorry. So here's the next topic, that is analog signal and digital signal. Analog signals are analog signals continuously vary with time. That is, analog signals are a continuous function of time. That's why analog signals are represented by a sine wave. Whereas digital signals are discrete in value and time. If you want to get a digital signal, then you have to make a unique combination of highs and lows. High is denoted by ones and lows are denoted by zeros. This unique combination of highs and lows gives us a particular information. An example of a digital signal can be the on and off switch. It's either on, that is high, or either off. There's nothing in between. And if we talk in terms of the noise, if there's a slight fluctuation in the signal, then a noise is created in case of analog signal. But for digital, fluctuation does not create any noise. I hope it's clear. Okay. So the next topic is the development boards. A development board is a printed circuit board that consists of a processing unit and a minimal logic support. The most commonly used development boards are Arduino Uno, Raspberry Pi, and Node MCU. The reason that we need to learn the differences between three is that the features of all the development boards are different. We need to have some knowledge of at least the commonly used boards so that we can find the most suitable board for our task. So we'll compare Arduino Uno, Raspberry Pi, and Node MCU. Arduino Uno and Node MCU are microcontroller development boards. while Raspberry Pi is a microprocessor development board. The next criteria for differentiation is logic level. A logic level refers to the low or high state of a development board. That is, when we say that the logic level of Arduino Uno is 5, what we mean is when you set the pin high, it will measure 5 volts. Similarly, logic level of Raspberry Pi is 3 volt and logic level of Node MCU is 3.3 volt. C and C++ are the languages that are used in Arduino Uno, whereas Raspberry Pi supports its own Linux-based operating system. And Node MCU is programmable with Arduino IDE. IDE stands for Integrated Development Environment. Next point is internet. If we need to connect Arduino Uno to the internet, we'll need additional modules or shields. Whereas for the Raspberry Pi and Node MCU has a built-in Ethernet port and Wi-Fi support. As for the cost, Arduino boards are cheaper. They cost around 500 rupees to 1000 rupees. Raspberry Pi are way much expensive than that. They cost in between 4000 and 10,000. And Node MCU, like in generally speaking, they are cheaper than some Arduino boards. As for the drive strength, Arduino Uno has a current drive strength means the amount of current that the board can handle. As for the Node MCU, it cannot operate with higher current that is more than 12 milliampere. But Arduino Uno can handle the current of 40 milliampere. The next point is clock frequency. The clock frequency of Raspberry Pi is the highest, that is 1.5 gigahertz. Then there's Node MCU with clock speed of 80 megahertz and Arduino Uno with the clock speed of 16 megahertz. It means this processing speed of Raspberry Pi is the highest among all. So if we need to do a task which needs very high speed processing or a complex task, then Raspberry Pi is preferred over Arduino Uno or Node MCU. As for the RAM, the RAM of Raspberry Pi can support up to 8 GB of external RAM, whereas Arduino Uno or MCU can support like a very RAM of Arduino Uno is 2 KB and that of Node MCU is 64 KB. Then the number of GPIO, that is general purpose input output pins. Raspberry Pi has large number of GPIO as compared to Arduino Uno and Node MCU. Like for Raspberry Pi, there are 40 pins and out of that 26 pins are general purpose input output pins. And when it comes to like difficulty to learn, Arduino Uno is very beginner friendly and it has many tutorials available on the internet, while Node MCU doesn't have many tutorials available on the internet, though it is easier to handle. We will move on to the next slide. So this is the Arduino board. I'll tell you about the pins in the Arduino board. So we have 14 digital pins, like right here, 0 to 13, out of which 6 are PWM pins. PWM stands for pulse width modulation. These are the pins we use when we need an analog output. Like here are the pins, the 11th, 10th, 9th, 6th, 5th and 3rd. These pins are PWM pins. And here A0 to A5, they are analog pins. Then there's a V-in pin when we need a power supply of 7 volts to 12 volts. For power supply, we can use this USB port or even this socket. Through this, we get a power supply of 5 volts. Then there's a reset pin. It resets the code. The code starts running from the start. And then there are these pins. SPI interface. SPI stands for Serial Peripheral Interface. It is an interface that enables serial exchange of data between the two devices. By serial exchange of data, I mean 1 bit at a time is exchanged. Then there is I2C, that is Inter-Integrated Circuit, and UART, that is Universal Asynchronous Receiver Transmitter. All these enable communication between the microcontroller and another device. These are called serial communication protocols. So these are the pins for I2C, then the pins of SPI. So we will move on to the next one.
Yeah, so till here, if there is any doubt, and I would like to conclude the difference between development boards. Can you go back, Tamanna?
Yeah.
Yeah, here. So if there is any doubt from this section or the previous sections or digital analog signal, microprocessor, controller, or anything till now covered, please let us know. Just unmute yourself and speak up. Okay, if there is nothing, then I will just give a brief conclusion about these boards. So Arduino and Node MCU are microcontroller type development boards, and instead Raspberry Pi is microprocessor type. So the time when we use Raspberry Pi is when we have a complex sets of codes that we have to run, and it needs to be very high processing power to process all these things. Then only we go to Raspberry Pi, but in general we use Arduino Uno or Node MCU. And as you can see, like the clock frequency is 60 megahertz in case of Arduino. In case of Node MCU, it's 80 megahertz. It's more than Arduino, but yeah, it's kind of comparable. But if we go to Raspberry Pi, it's way more than that. It's 1.5 gigahertz. But if you talk about flash memory again, in case of Arduino, it's just 32 KB. In case of Node MCS 4 MB, it's high. It's very much high. But if you talk about Raspberry Pi, then it can support way more than that. In case of RAM, it can support up to 8 GB RAM. The Raspberry Pi. And then Arduino Uno is kind of very simple. There are so many tutorials available. So we start with Arduino Uno, and that's what we are going to do in this session as well. But if I talk about Node MCU, then it's kind of same with Arduino Uno. Even it's in terms of cost, it's am I audible?
Yes.
Okay, I don't know why someone muted me by mistake. So I was saying about the cost thing. So yeah, so then Arduino Uno, we have so many tutorials for Arduino Uno. That's why we generally go for Arduino Uno. But in case of Node MCU, it's also kind of similar. Even we can program Arduino. Okay, is what is this happening? I don't know why someone is muting me again and again. Yeah, okay. So Node MCU is cheap, and but since there are not so many tutorials available for it, so we generally don't go for Node MCU at first. We first try Arduino Uno, and we begin with it. If I talk about programming of these things, so Arduino Uno and Node MCU programming is totally same. Even we can program Node MCU in the same environment, that is Arduino IDE, that comes with Arduino or Arduino Uno or other Arduino boards. So programming for Node MCU and Arduino Uno is totally same. But in case of Raspberry Pi, it's different. We have to code in its own Linux-based operating system. And then if I talk about GPIO pins, general purpose input output pins, where we give input to our microcontroller and it takes output. So these are quite in large number in case of Raspberry Pi. In case of Arduino Uno, it's lesser than that. But if we want to use Arduino versions of microcontrollers or development boards, then we do have another kind of boards, that is Arduino Mega also. So if we have a criteria of more number of pins, then we might look into some Arduino's other version, that might be Arduino Mega also. In case of Node MCU, yeah, so it's generally very less number of pins, even it's lesser than the Arduino Uno. So we might not prefer Node MCU in case we want to go for more number of sensors or anything as such. Yeah, that's it, I think. Yeah, next slide. Great. So I'll just give you a brief idea about some coding commands that we definitely are going to use when we code anything in Arduino. So the first thing is pin mode. So first we have to define whether we are going to use any pin as input, output, or input pull-up. Input pull-up will be explained later. But first we have to define whether we are going to use this pin that we'll be using, whether it is an input pin or we are going to take any kind of output from that. We have to define that first. And then there is this digital write. So how do we use it? It's nothing but we are defining high value or low value to a particular pin that we have already defined as output pin. So this is how we use it. And the way I have written, it's syntaxically correct. Like I have written digital and then W as capital. So this is the exact syntax that has been written here. For digital read, we just have to provide the pin number that we want to read, whether this pin is high or low. And then if we come into the analog part, analog signals, and there is this analog write. So how do we give an analog signal is we use PWM waves, that is pulse width modulation. That will be what this thing is, that will be covered later part, but I'll just give you a brief idea about them. So we give our analog output through this analog write. We define pin and then the value. And this value ranks from 0 to 225, and this 0 to 225 is being mapped to 0 to 5 volt. So say if we are giving here 225, then the voltage that will be coming out will be 5 volts from that pin. And in case we are providing 0 here as a value, then the 0 volt will be coming out through that pin. So we can just map this 0 to 225 to 0 to 5 volt. And according to that, the voltage level will come. So it's generally being used for any variation in brightness or speeds of motor, etc. In case of analog read, according to the logic level of development boards. In case of Arduino Uno, that's 5 volt. So we just give the number of, the value of pin that can be A0, A1, A2, A3, up to A6, A5. So this is how we read the analog signal through this command. If there is any doubt in it, you can ask. Okay, fine then. Yeah, Taman, I think we can go ahead.
What is input pull-up?
Yeah, okay. So this thing will be what, like this input pull up and input pull down. This will be covered later part by error as I mentioned, because we have to like tell you what this pull up thing is happening, and then it's a bit we have to elaborate on this. So it will be covered later.
Okay.
Yeah.
Okay. So now we'll do some Arduino programming in TinkerCad. I'll share the screen once again. Is it visible?
Yeah, it is.
Okay. So on the right side, here are all the components, and here's the code.
Just to give you a brief idea what this TinkerCad is, it's nothing but the simulation software for Arduino and related stuffs. So we can simulate our circuits and get an idea what will happen if we do these things physically. All these things.
So now we'll grab.
Go ahead.
Okay, we'll grab an Arduino. Also, here are all the pins that I told you about, 0 to 13 digital pins, the PWM pins. These are the analog pins, A0 to A5. And there's V in. This is the USB socket. So what we'll do is, we'll do the blinking LED project. So for that, we'll take an LED. We'll join the cathode to ground. You just have to click the ends of the components to get this wire. And then we'll use a resistor. A resistor helps in limiting the current. Without it, there's a chance that LED will burn itself out. And we'll join the other terminal to pin 13. The other terminal of the resistor to pin 13. So now we'll start with a code. So this is the basic syntax. Whatever is written here in the function void setup will be executed just once, while whatever written here in void loop will be executed again and again. So we'll be setting, okay. Look, this is a built-in LED. This is connected to the pin 13, and we have connected the anode of our LED also to pin 13. So when it says built-in LED, it's talking about pin 13 only. Okay, so we'll put the pin 13 for the output, and then in void loop we'll use the function digital write and make the make pin 13 high. That is, the LED will begin to glow. Then we'll use delay to wait for 1 second. Here 1000 means 1000 milliseconds. We'll use delay, then wait for 1 second. Then again we'll make pin 13 low. Now the LED will stop glowing. Then we'll wait again for 1 second. Then this will repeat again and again, and this is how we'll make the LED blink. So we'll start the simulation. And the LED is blinking. So do you want to ask anything, any doubts? Okay, then we'll move to the next topic.
Can you show the code part? Yeah, okay, great.
Okay. Shall we move?
Yeah. There is some echo.
Code part, I mean, when I open the code part, I'm not able to see the coding screen. It is
Okay.
showing the built-in and this one, but
What happened, Shrija?
like that coding part, I'm not able
Yeah.
to see the code screen where you write the digital write and stuff.
Like go here, go. There's a box on the left.
Yeah, blocks plus text is it?
Yeah, blocks plus text.
Right. Or just text is also fine. Right.
Okay.
Yeah, right. Yeah.
Yeah, that's also fine.
Please. Okay.
Yeah, Tamanna, could you show the screen once again? I want to explain certain things. Yeah, okay, great. So if you guys see in the void setup, we have put the mode of pin, and in the void loop, we have put that code that we want to run again and again. So if you see there is this digital write LED we have defined, and then we are calling it as high, and we are waiting for 1 second to let it be in that position, and then we are going to make it low, and then wait for 1 second, and then again make it high, and that's how it's going in the loop. So what happens is when we start our code, so if there is anything from if there is nothing in outside these two functions, if there is nothing above void setup, then our code just jump into this function that's called void setup. So we define our pins, we initialize certain things or anything that we want to run just once. So we put all those things in void setup, and if we want to include any kind of libraries, or if we want to define any data types, any variables, then we put it outside any function. So the part where if you have seen the C++ code is written, so in these lines or outside these two functions, we define those things. I think you will see all these things in detail in the later part, but yeah, I just explained a little about that. Yeah, Tamanna, you can take it.
Now we'll look at the data types. the data types specify which kind of data you want to store in a variable. I guess everyone might be very familiar with it. Like the int data type, it takes space of 2 bytes and it can store a number between minus 32,768 to positive 32,767. Then there's unsigned int. It's just like int, but it can't store negative values. So it will store values between 0 to 65,535. Then there's long. It takes up more space. That's why we can store a large number of numbers, larger number of numbers as compared to int or unsigned int. Then there's unsigned long, which is same like long, but we can't store negative values. Its range is between 0 to 429. Then there's float for storing decimal values, char for storing alphabets like capital ABCD, small ABCD, and the string. Other space needed for string depends on the length of the string. Like a string is basically a set of characters. So the more the characters, the more space it will need. So here's the syntax as to how to initialize one. We write the name of the data type, then we'll write the name of the variable, like whichever variable you want to choose, and then we assign it a value. Like for example, here we are assigning a value
You got muted, I guess, Tamanna.
hello.
Yeah, you're audible now. You are explaining this integer a is equals to.
Since when was I muted?
This integer a is equals to 9. Example.
Okay. So we have to store a value 9 inside a. 9 is an integer, so we'll use the data type int. Then the variable, and then we'll assign it a value. So sorry for that. So now this is how we initialize variables.
Yeah, right.
Okay.
So
Now Ira will take forward.
if there is any doubt till now, please ask. Okay, then I think Ira, you can take forward.
So I hope my screen is visible.
Yeah, indeed it is.
Okay. So hi everyone, I'm Ira Rai and I'm pursuing my BTech in Aerospace Engineering from IITM, and I'll be taking forward this session by introducing you these two topics. So we'll study about proximity sensors, then motors, and introduction to Arduino and TinkerCad. So let's start with proximity sensors. So what are proximity sensors? So these are the sensors basically which detect presence of nearby objects within a specified distance. So the distance can vary from sensor to sensor. It can be from like 2 inches to 10 mm or 30 mm. So without any physical contact. So because of this very reason, these sensors are highly reliable and they have a long functional life. Also, none of the proximity sensors include any moving part. So because of all this, they have long functional life. And proximity sensors can be found in our daily life applications, like, for example, in our smartphones for emerging from sleep mode. Whenever some notification or something comes and we put our smartphone in front of our face, so we are able to see the notification and the phone emerges from the sleep mode. So that's because of proximity sensors. Also, in robotics, you can see proximity sensors for detection of obstacles. For example, in this image, this is a robot, and we have 5 proximity sensors here. So it is useful in detection. And also, like, for example, in parking areas for safe parking. So while backing a car, we would need some alarm, some detection that we should not back some further from some threshold limit. So we would have a proximity sensor which would send the output if the we are backing the car more than some limit. So it would send the output, electrical output, to some buzzer, and the buzzer would ring. So that would alarm us that we should not back it further. So in our daily application, these are some of the examples of proximity sensors. So we have various types of proximity sensors, but these are our 5 major types. So first we have acoustic or ultrasonic proximity sensor. Then we have photoelectric, capacitive, inductive, and magnetic. So in this images, this is a capacitive proximity sensor. This is ultrasonic, and this is photoelectric. So we'll study their basic principles one by one in brief. So acoustic proximity sensor or ultrasonic. As you can see in this image, this is an ultrasonic sensor. So they are useful for object detection over some intermediate distance, some feet. And they're also useful for measuring distance because it can calculate the total time taken, and the distance can be calculated by this particular formula, that is speed of sound into total time taken divided by 2, because the pulse goes and comes back. So the distance is 2 times. Also, the working principle is quite simple. It consists of 2 transducers in which one emits and the other receives the ultrasonic wave and converts it into electrical variation of some frequency. So next we have photoelectric proximity sensors. So they also have almost the same working principle as acoustic sensors. So they are useful in detecting objects and change in surface conditions also through optical properties. So their working principle involves an emitter and a receiver. So an emitter emits the light and the receiver receives the light, and so it gets interrupted or reflected by the sensing object. So it changes the amount of light that arrives at the receiver. The intensity of light, it gets changes. So this change is detected by the receiver and it is converted into an electrical output. So this part is same for all the proximity sensors. Some change is detected and it is converted into some electrical output. So some of the pros we have for these sensors are, it has long sensing distance that is greater than 10 mm. It's comparatively long, and it can detect any object. So the detection is not limited for some specific objects, like we'll study further. The inductive proximity sensors can detect only metal objects. The magnetic proximity sensors can detect only magnets, but it has no such limit, so it can detect any wood, plastic, or any sort of object. Also, it has a fast response, so it is obvious as because we know the speed of light is quite huge in 3 into 10 to the power 8, so we get a quick response in these sensors. And also it can detect colors. This is quite a unique property of this sensor, because as the emitted light will strike the target, so according to the color of the target, some particular frequency will get absorbed, in some particular frequency will get reflected, which is received by the receiver. So in this case, that change is detected by these sensors. So these are some of the advantages of these sensors. Let's go to capacitor. So capacitor proximity sensors. So every sensor notes some change, and in this case, some change in capacitance is read by the sensor. So it is able to detect objects through non-metallic walls with its wide sensitivity band. Like all the other sensors, this also has a long service life due to absence of any moving part or any physical touch also. So in this case, we have mainly two types of proximity sensors, capacitor. So one is dielectric type and the other is conductive type. They have a little different working principles. So we'll first study the dielectric type capacitive proximity sensor. So the capacitive proximity sensor, this consists of a high frequency oscillator along with a sensing surface formed by two metal electrodes. For example, like here you can see this image. So we will have two metal electrodes here and electric field would be there between these capacitance. So as any object would approach this, so in this case, in the case of dielectric type, our only condition is the object should have a higher dielectric constant than air, so that there is sufficient change in the electric field between these capacitances. So as the target will approach, there would be some change in the electric field, and this change is detected by the sensor. So as a result, as this target approaches, the oscillator circuit starts oscillating and changes the output state of the sensor. So when some particular amplitude is reached by the oscillator circuits are generally like of LC type, and as the object moves away from the sensor, the oscillator's amplitude decreases. So this switches back the sensor to its initial state. So also, if we would go back, so when an object comes near the sensing surface, it enters electrostatic fields of electrodes and changes the capacitance of oscillator, as I explained it right now. So the typical sensing range of this kind of capacitor is few to 1 inches. Also, in like modern capacitive sensors, the range can be extended up to 2 inches. So, as I said, if the target has a larger dielectric constant, it can be detected quite easily. Also, this is a schematic representation. Like electric field is there when there is no target, and when the target approaches, the electric fields increase. A change is detected, and this change increases the amplitude of the oscillator, which further sends the output to the sensor. So this was our dielectric type capacitor. So again, what was the basic principle? It was the dielectric increases electric field of capacitance. So this is the main property that is utilized in this type of sensor. So let's go to the conductive type. So in conductive type, the property utilized is this. Capacitance varies with distance between its two plates. So in this case, we do not have any metal electrodes here, but instead one of the plates of sensor is one electrode and the target acts as another electrode and a second plate of capacitor. So one plate of capacitor is inside the sensor and the other plate is the obstacle or the object. So this now the air between is the dielectric medium. So in this conductive type, as the object approaches the sensor, some capacitance would be there and the distance decreases, so the capacitance increases. Again, the oscillation would increase up to some amplitude and some output would be sent, electrical output. So, and if the target moves back, if the target moves back, the distance would increase, that would decrease the capacitance, and that would again decrease the amplitude of the oscillator, and it would bring back the sensor to its original state. So these are the two properties that are applied in these two types of capacitive proximity sensors. So now we have, I hope it's clear till now. We discussed three types of sensors: capacitors, photoelectric, and acoustic. So these two had basically same principles. This one had a little different principle. So I hope it's clear. So let's move on to inductive proximity sensors. So this sensor operates under the electrical principle of inductance. Like it follows the Faraday's law, where a fluctuating current induces an electromotive force in a target object. So these non-contact proximity sensors detect ferrous targets, which is obvious because uh, we have a oscillating magnetic field here. Because we want the magnetic field to be variable. So according to Faraday's law, the metal in a variable electric field will have induced currents. So these currents are called as eddy currents. So let's see here the working principle. So the oscillator creates a symmetrical oscillating magnetic field that radiates from ferrite core and coil array at the sensing surface. So when a ferrous target, so this type of sensor is limited for ferrous targets or metal targets because only they can produce eddy currents. So when this enters the magnetic field, small independent electrical currents, which are eddy currents, are induced on metal surface. So what happens is this: when these eddy currents are produced, some magnetic fields due to these currents also is induced, and this is in opposite, in reverse of the incoming magnetic field. So because of this, the intensity of this magnetic field decreases, and again this change is detected by the oscillator, whose amplitude again increases or decreases respectively, and the final electrical output is sent to the sensor. So basically, again, this is the change that is observed by the sensor. So due to this, load will be caused on the sensor that decreases electromagnetic field amplitude, as I explained. So these sensors have high switching frequency. They are useful in metal detection in harsh environments, and the detection range can be 60 mm. So these both are the most similar representations of what I just explained. So we can move further so we have next magnetic proximity sensors. So these sensors are specifically designed to work with magnets. So they have high mechanical stability in shock and vibration conditions. So magnetic proximity sensors have various type of technologies, but in this slide I'll be just explaining two types, that is reed switch and the Hall effect sensor. So reed switch or like reed sensors make use of reed switch. So they use a magnet or electromagnet to create a magnetic field that opens or closes a reed switch within the sensor. So basically this is a reed switch, and we have two ferrous objects here, or two ferrous rods here. So as when there is no magnet, the rods are apart. But as soon as the magnet approaches the reed switch, the magnets are joined. The switches are joined. So it contains two ferromagnetic nickel and iron reed elements, which are these, in an evacuated hermetically sealed glass tube. Hermetically sealed glass tube is just an airtight glass tube. So to minimize contact or arcing, when a magnet approaches the switch, the magnetic forces closes the reeds. So these are called reeds, these ferrous reeds. So in presence of a magnet, these reeds are closed. So it obviously detects the presence of a magnet. So next we have Hall effect or Hall effect sensor. So it is a type of sensor which detects the presence and magnitude of magnetic field using the Hall effect. So I hope you all remember what the Hall effect was. It when a thin rectangular plate was placed, and it was connected with a voltage and some magnet with static magnetic field is brought closer to it. Then there was induced electric field. So this was the Hall effect. So Hall effect sensors respond to static, non-changing magnetic fields. So this is an important difference. Like this is the key difference from inductive sensors. So in case of inductive sensors, the magnetic field was variable, which was important for the production of eddy currents. But in this case, the magnetic field need not be variable. It is static, so it can detect magnets easily. So this is what a Hall sensor looks like. This is the Hall effect. Uh, so this was all about the proximity sensors. We discussed 5 types of proximity sensors and their basic principles in brief. So I guess we can move on further with motors. So the classification of motors that we'll be studying here is in regard with its application in robotics. So we won't be studying like AC motors or DC motors, but we have classified it as servo motors and stepper motors. So this is in regard with its application in robotics and some electronic stuff also. The basic principle is same. It converts electrical energy to mechanical energy. So let's start with the servo motors. So this is what a servo motor's cross-section looks like. We'll study in more detail here. So a servo motor is a type of motor that can rotate with great precision. So when we want a robotic arm to move by some 30 degrees or by a little bit like by 10 degrees, we want its fingers to move or rotate by some 10 degrees. So we can't use a AC or DC motor in that case. So we need servo motors. We need great precision of motion, great precision of. So we need servo motors. So normally this type of motor consists of control circuit that provides feedback on the current position of motor shaft. So this feedback allows servo motors to rotate with great precision. I'll be explaining more about this control circuit in the next slide. So the basic working principle is, so these servo motors basically consist of a simple motor. So this motor can be AC or DC motor. Then we have a gear assembly and we have a potentiometer and a shaft. So a servo motor is a closed loop servo mechanism that uses position feedback to control its motion and final position. So the input to its control is a signal, either analog or digital, representing the position commanded for output. I'll be explaining more of this in the next slide. So as you can see, this is a robotic arm and we have 6 servo motors working here for every joint, for every rotation of joint. So let's see here. So this is the mechanism that I was talking about. So this is a microcontroller. So this can be any microcontroller. So Arduino is also one kind of microcontroller. So this gives the command or whatever the code we have uploaded. So like we want the DC motor, the motor to rotate by 30 degrees. So we have uploaded that particular data here, and this data is transferred to servo controller or this control circuit. So this control circuit transfers the data to the motor, and the motor rotates by the given angle by 30 degrees or any input angle that we have written here. So this is a closed mechanism, this whole mechanism. So this data again comes back to the control circuit, and then the control circuit keeps the motor in that state, at the state of 30-degree rotation. It stops the motor at that state. So we have the data comes back to the control circuit. That's why it is called as position feedback. So this is the servo motor case, and this is its basic working principles. So let's move on with the stepper motors. So this is how stepper motor looks like, and this is a cross section of it. So a stepper motor, first I like to explain it through this diagram. So we have a stator here. These are called stators, and we have windings in these stators, right? And this is a rotor. A rotor can be any permanent magnet or any electromagnet. So these stators, so when we pass current through these stators, but in this case what happens is we do not pass current simultaneously into all the stators. For example, this stator is connected to some switch, and I close that switch and current is passed into this particular stator. So this gets energized, and because this is a magnet, some torque is created, and because of that the magnet aligns. Suppose if this is north and this is a magnet with some south here, so it aligns along this stator, so by moving 90 degrees. So if this is the initial state, and suppose we have a stator here, and if again this switch is closed and this particular stator is energized, this magnet will align itself along this stator. So if you can see, if I align this particular stators one by one, if the switches are closed one by one, so this particular rotor will align itself to the stator according to which one is energized. So what is happening is it is stepwise rotation. So it is rotating stepwise. Also, these kind of stepper motors, we play with phases. Suppose these two switches are closed and current is running into these two of the stators. So these two will be energized. So what will be the position of the rotor? It would be between these stators. So it would be some different angle. Suppose 22.5 degrees, or if stator is here, then it would be along this line, which is 45 degrees. So we can align it along to our angle of our desired final position of our. So a phase difference of 90 degree would rotate it to 45 degrees, and so. So let's study through this now. So it is an electric motor whose main feature is that its shaft rotates by performing steps, as I explained just now. So by moving by a fixed amount of degrees, stepper motors have a stationary part, which is the stator, and the moving part, which is the rotor. In this case, you can see this is the rotor, which can be a permanent magnet or an electromagnet, and this is a stator with windings in it. So on the stator, there are teats on which coils are wired. So for the proper positioning of the coils, teats are there. So while the rotor is either a permanent magnet or a variable reluctance iron core, that is an electromagnet. So the basic working principle of stepper motor is as follows. I just said, energizing one or more of the stator phases, a magnetic field is generated by the current flowing in the coil, and the rotor aligns itself along that field. So by supplying different phases in sequence, the rotor can be rotated by any specified amount to reach the final position. This is all just that I described. So in case of stepper motors, we can find its application in like digital cameras or even in robotic arms, and even many machines also in industrial. It is quite useful motor in regard with industrial purposes. So move on to introduction to Arduino with TinkerCad. So as explained earlier, TinkerCad is a simulation software, and before moving further, I would like to introduce some terms, some important terms. So this is already known. Arduino is a microcontroller development board. This is already been explained, so I'll just move on. So duty cycle. So
Yeah,
duty
okay.
cycle.
Sorry to interrupt you, Era. I think we can have a break of 2 minutes so that we can have some water. And if there is any doubt till now, you guys can ask.
Okay, sure.
Yeah. Yeah, if there is no doubt as such, I think we can start.
Yeah, okay. So I was explaining duty cycles. So duty cycle in a signal, it is the fraction of one period in which a signal or system is active. So as we can see in this rectangular wave, um, this portion represents, like in digital, this is a digital signal. So this is 1, this is 0. So this is the active state of the signal, and this is the whole time period of the signal. So the fraction of the active state upon the time period is the duty cycle. So it is commonly expressed as percentage. So now the baud rate. So this would be useful in when I'll be discussing the TinkerCad software. So the baud rate is the default rate in Arduino. This is 9600 in case of Arduino Uno. So this means the serial port is capable of transferring a maximum of 9600 bits per second. So this is like the rate at which the data is transferred, and this is 9600 in case of Arduino. And the serial port, it is the communication between Arduino and our computer. So in case of Arduino, we have one serial port, which is UART. So let's go to what is PWM. So PWM stands for pulse width modulation, and it is a technique for getting analog results with digital means. So the duration of on time is called pulse width. So to get varying analog values, we change or modulate that pulse width. So to get an idea of PWM, I can like an example we can have is like a servo motor. So a servo motor rotates between 0 and 180 degree. A servo motor cannot rotate 360 degrees. So as the value is limited to 0 and 180 degrees, so when we attach it to some pin, so it will take two values, 1 and 0. So it is either 0 or 180 degrees, but what if we want the angles between them? So we want some analog results with digital means. So that is the job that PWM does. So when we are connecting servo motors to Arduino, we connect it to PWM pins. So as told in earlier by Tamanna, we have 6 PWM pins. So these are 3, 5, 6, 9, 10, and 11. So we will connect the servo with one of these pins because we would want the angle to be either 30 degrees, 60 degrees, or any other amount, not just limited to 0 or 180 degrees. So this is the use of PWM pins. So generally you can find an Arduino board by approximate sign. So like if you see here, so these are 3, 5, 6, 9, 10, 11. You can see this approximation sign in front of these pins. So these are PWM pins which will give us analog results with digital means. So next we have pull up and pull down resistors. So when our pins are not connected either to the ground or to any voltage, so what is the state of that pin? It is neither high neither low. So what's the state of that pin in that case? So that state is the floating state of the pin. So as we see, pull-up and pull-down resistors are used to correctly bias the inputs of digital gates to stop them from floating about randomly when there is no input condition. So when we have no input condition, it is neither in a ground connected to ground or any voltage, and we don't want that floating state of that undefined state of the pin. We make use of pull-up and pull-down resistors. So that floating state of pin is undefined because there can be any kind of thermal noise, electrical noise, or electromagnetic disturbances also. So because of all this reason, the pin state when it is not connected is undefined. So we want to avoid that state, and so we make use of pull-up and pull-down resistors. So pull-up resistors. So a pull-up with a pull-up resistor, the input pin will read a high state when button is not pressed. So whatever is our input pin, it will read a high state when we have not pressed the switch. So a small amount of current is flowing between VCC and the input pin. So for a more proper explanation, you can see here. So this is our pin, and we have a pull-up resistor here. So initially the switch is open and it is in a high state. as it is connected to VCC. So when the switch is closed, the pin gets into a low state. As we hear, when the button is pressed, it connects input directly to ground. So because of this, input pin reads a low state. So this was our pull-up resistors are much more in use than pull-down resistors. So a pull-down resistor is quite opposite of pull-up. So in this case, the initial state is of low logic level. So the wire is at a defined low logic level, even when there are no active connections. So pull-down resistor holds logic signal near to 0 volts, where no active device is connected. So it pulls the input voltage down to the ground to prevent an undefined state of the input. So this is a pull-down resistor. As you can see, initially the switch is open and it is connected to the ground. So initially this is at low state. And when the switch is turned on, it goes into the high state. So this was about the pull-up and pull-down resistors. So I think now we can go to Arduino and TinkerCad simulations. So I hope everybody has logged into TinkerCad. So I'll be switching.
Yeah, so before we move ahead, there was some doubt regarding input pull-up. So that we define in the pin mode. So if you, I think you have already seen this PWM and the input pull-up thing. So how this happens? So what we do, we define a particular pin as input, and also we make that as high in default. So that's what we are doing when we are defining a pin as input pull. Yeah, so if there is any doubt, you guys can ask. Otherwise, you can just go to the TinkerCAD and try out some interesting projects. Ira, in case you're talking, you are muted.
Okay. So, fine. So this is our TinkerCAD as seen earlier. So here we have many electrical equipments which we can use. So first, in this project, I like you to know about serial monitor and how we can give inputs to serial monitor. So serial monitor is something that when our code is running, it tells us like what is going on with the code. So like, so we can take an Arduino here. So this is our Arduino. And now I'll code. So first I'm declaring, first I'll write a little and then I'll explain. So there, this is a very short code that I've written. This is just for the explanation of serial monitor. So, okay. So first what I've done is I have declared a variable which is input byte. You can give any name. I have given input byte. So I've declared this as an integer data type, and then so this variable is a global variable. Global variable is a variable which is not like I've not declared it within any function. I've not declared it within void setup or word loop. I've declared it globally. So the use is that I can use this variable inside any function or even outside any function. So it doesn't destroy that variable. But that is, if we declare any variable inside some particular function, so it won't function outside that particular function. So the variable can't be in any use. It makes no sense or to use that particular variable outside the function because it is declared within that function only. So that is a local variable. So I've defined this variable globally, and then in void setup, I've written serial.begin 9600. As I've said, 9600 is the default baud rate of Arduino. This is the rate in bits per second at which the data is transferred. So serial.begin begins the communication between Arduino and our computer. So after this, then in word loop, I have written
Just to
serial.available.
Hira, just to make them clear, so in case we have a physical Arduino, so what will happen? We'll connect that Arduino through a data cable. So how are we
Yes.
going to communicate and transfer our commands into Arduino? We'll use this thing called serial port and connect our Arduino through a USB port. That's what. But in case we are simulating, so everything is on this computer screen only. Yeah, just to make them clear how it works in real when we have physical Arduino.
So as like you said only, we have a USB port for a physical Arduino which is connected through this, and then I'll move forward with the code. So in word loop, I've written serial.available. So this particular function basically is to check whether there is data received or already stored in Arduino. So if serial.available, so if the data is there, following commands are followed. So input byte, the variable that I've declared, I've written it equal to serial.read. So serial.read is a function which returns first byte of incoming serial data available. So I'll be giving some input in the serial monitor and it will read the data. So then we have serial.println input byte. So these functions, these both println and write will show some output in the serial monitor. So we can write here print also instead of ln, but then as you see, all the output would be in the same line. But if we want the it to be from the next line characters, so we write ln. Also, it is a much neater and clearer way to visualize the data. So I've written serial.println input byte. So serial.write input byte. This is serial.write is also a function. So it writes binary data to serial port. Whereas in this case, println it writes data in human readable ASCII form. So it will print the data in ASCII form, for example. So for writing comments, we use these double slashes. Right. So we'll observe this. So this is our serial monitor. So I'll click on it. So I'm starting the simulation. Okay, there seems to be some error. Just a minute. Okay, there has to be small b here.
You didn't include the if like.
Yeah, I didn't close the bracket here. Okay.
Yeah.
So fine. So right. So if I write 0 here, if I send 0 as an output, so this is what we get. So we got 0, the binary number that we entered, and this 48 is the ASCII value of the 0. So what is the ASCII value of the 0? There's an ASCII table that I'll have to log out to show you, but I'll show you once the ASCII table. Just a minute. This is an ASCII table. So as you can see, the corresponding ASCII value for 0 is 48. This is 0, and this is the corresponding ASCII value for 48. So similarly, if we would have entered 1, we would have got 49. So also we can work with characters and strings also, that we'll see now. Right, so similarly, if I stop the simulation and clear and start it again, so if I enter 1 here, we'll get 49. This is the corresponding ASCII value for 1, right? So suppose now I want some ASCII value of some character. So what I'll do, I'll change the data type here. I'll change it to character data type. When I do that, and then I'll start the simulation. So suppose now I write here A. So we are getting A only. But it should come some ASCII value, okay? So there should be start the simulation. We have defined character and okay, right. So like here I've like incremented the input value by 1. So when we add double plus, so it increments the value by 1. So if I'll type A here, then in serial.write the value printed should be B. So let's see. Okay.
There should be semicolon. Yeah.
See here. So like I had given the input A. So the corresponding, suppose the ASCII values, I'm just for supposing purpose, suppose the ASCII value is something like 79. So the input byte is incremented by 1, so it would be 80. And then serial.write prints the corresponding alphabet, which is B. So the ASCII value of this B would be 80 and A would be 79, as I had incremented this particular part. So we can play with this serial monitor a lot. We can give it any string value, any character value, or any integer value. Also, for more complex circuits, we can give inputs to the serial monitor, and let's stop this animation. So we can give inputs to the serial monitor. Suppose we have a RGB LED, and we want and we have given input red. So when we are giving input red, we want the red LED to blink or to glow. And if then we are giving input green, so we want that particular color of LED to glow. So we'll check that. We'll check that out. We'll check that project. So I'll change. So okay. So we already have a project here. So what we have done here is, I'll just explain. So we took an Arduino from here, and this is a breadboard. So when we want to connect many wires from the electrical equipment, we make use of breadboard. So for various connections, for multiple connections, so we have taken a breadboard here. It's just the purpose is just to serve various connections. So like in this case, if we want to connect this wire to ground, so we can connect this wire to any of these points. So it also makes the circuit much easier to assess, and it makes it quite clear. And so any of these points can be used for connecting into ground. And so this is an RGB LED. It's available here. If you just search for it. So this is an RGB LED. We already have it, so I'll just delete it. So this RGB LED, we have fixed it to our breadboard, and we have taken a resistor, which is just to prevent shorting. So we have connected, this is red, this is blue, and this is green. So we have connected it to the pins in Arduino, to the digital pins in Arduino. So we have connected red to the digital pin 12, and we have connected blue to the 11th digital pin and green to the 13th. So these were the necessary connections that we had to make. So after making these connections, we have to write the code, and we have to write code such that whatever input we give, that particular color is glows into the LED. So, for example, this. So this is our code. So we need to first declare the variables. So we are declaring our first variable red, which is connected to the 12th digital pin, green to 13th, and blue to 11th. All of these are integers. So our data type is int. And then we have declared a string also. String is just a sequence of characters. So string, we have declared color as our string. Okay, so this is just to initialize the string. Initializing purpose is just that it should not have some previous value. To just start from the 0th level, our reference level, we initialize any integer or any variable. So in void setup, we have declared pin mode. So our pin mode, and we have declared the value it is going to take the output. So it will be taking output instead of input. So our pin modes are red, green, and blue because we want the output. LED will be glowing, so that's our output. So these are our pin modes. Pin mode is a function. I hope it's known already. It configures the specified pin to behave as an output or an input. The function of pin mode is just this. Then again, to begin the serial communication, the communication between the Arduino and the computer, we initialize it with this command, serial.begin 9600, which is the baud rate. And then in void loop comes our main code, and it is in loop because we want it to be repeated. We don't want the code to just run once. We want the code to keep on repeating. So in void loop, we have if serial.available. As I said, serial.available is basically to check if data received or already stored. So if serial.available, color equals to serial.read string. So yes, so whenever we have our input as a string, as a series of character, for example, if I'm not typing any 0 or 1, any number, but I want some series of character like red, green, blue, hello, or any character, any string, so then our command of serial.read changes to serial.read string because we are reading a string, right? So color equals serial.read string. So now we the print. So whatever color we'll be typing here, that particular color will be printed onto the serial monitor, so that we know that this is the code. This is the color that is being followed. So we have written serial.print. You can write here ln also, but it won't make much difference here. So serial.print color. So we are delaying it by, so delay is a function. So delay is again a function which which tells us the time period for which the particular, after which after particular command it has to stop. So this by default is milliseconds. So delay 10 means 10 milliseconds stop would be there after these commands. So after moving further, if there are if-else conditions. So whenever we want some conditions, so we make use of if-else statements. So this is a part of C++ programming. So if means like if this particular condition.
Is your screen being frozen, or I'm just seeing the serial monitor? Is it same for everyone, or is it me only?
You can't see the code.
I think you should keep down the serial monitor.
Okay. The code is visible?
Yeah, now we can see the code. Yeah.
Right. So I explained the delay part. I hope that part is clear. Delay is just the time period for which it will stop. And then we have condition statements because we have a condition here. Like if I type red into the serial monitor, if the input given is red, then the red LED should glow. So we have a condition. So whenever this is the case, we make use of if-else statements. So if color equals to red, if this is the string that I have typed into the serial monitor, then digital write, these digital will give me the output. So I have given, you can write here high also, low also, but it has to be binary as it is digital pin. So digital write will give the output. So the red will be in a high state, that is in active state, which is state of 1. So I have written 1 here. So digital write, again green and blue should be 0. At the time I want the red part should glow, So I'm putting green and blue 0. So I hope it's clear digital right and all. It was explained previously also. It just assigns high or low to a digital pin. The only job is to assign high or low to a digital pin, and these variables are already declared globally above. So red corresponds to the 12th pin. So this 12th pin will be in a high state when red is entered. So after these commands, there would be a delay of 2000 milliseconds. And then again, we have written digital write red to the 0. So we are saying that when we write red, uh, it will glow for 2 seconds and then it will be in a low state. Like it won't glow any further after that. If we remove the statement digital write red comma 0, then the LED will keep on glowing red until we change the string to green or blue or just stop the simulation. So in this way, it will glow red. So first, I think we can see how is it working. So suppose I type red here. My input is red and my input is a string. So, okay, we haven't started the simulation. So in starting, I've typed red here and then see here, like, so the red part glowed for 2 seconds and then because of this command, digital write, where it is, so red comma 0. So because of this command, it stops glowing. So because I wrote red, the red part of the LED glowed. So let's stop the simulation, and the further part of the code is quite similar. Now this was the if-else condition. So this was the condition for if, like if I type red, then the red should glow. And else statement is if I do not type.
There's one thing. I don't think we need else after every if. It will work even if we
it's
are
quite
providing it in the end. Yeah.
Yes, because we have given separate conditions, so this part is quite unnecessary. So we can remove that part. So here also, this part is not required. So I'll just explain this condition for blue and green, which is quite similar. Again, if our color, if the string that I've typed in serial monitor, if it is blue, then which one should glow? The pin, this one, 11th pin. So for that I've written digital write blue comma 1. That means it should be in a high state. It should be in an active state. This blue pin, that is the 11th pin. So again, if the rest of the code is same only, I've delayed it again for 2 seconds. You can delay it by any number of any seconds. You can write here 1000 or 3000, any amount of time. So again, if I write color equals to green, if the string is green, then the green part would glow. So it would be digital write so this would read 1 here, so which is the active state. So we can just see here in serial monitor now what happens if I write blue or green. Starting. Suppose I write green here. So it will glow for 2 seconds and then it uh, switches off or goes to its low state. So again, if I type blue, again it was blue. And then if I type red here, it would be red. So this is how you can control the color, whichever color you like, by giving the input yourself with the help of serial monitor. So this is the use of serial monitor. This was one of the examples. I hope this is clear. The coding part is clear. We have just used some of the function. We have declared variables and we have declared integer and string variables. Then we have assigned the pin mode that is read as output, which is obviously this is output only. And then we have serial.begin to start the serial communication. And then we have used the if-else conditions in the word loop function. So I hope this part is clear. Digital write, it just assigns high or low to a digital pin. So not many functions were used here. So I hope this is clear. This part should be kept in mind, like whenever we are using strings, so we must write serial.read string. But in case of integer or even character, it works with serial.read only. We don't need the string part. So this was one of the projects, and let's move on to the last project for today. So in this last,
Ira, I don't think we'll be able to cover that up. The time is about to up.
okay,
So we'll see that tomorrow.
tomorrow, Saturday.
Oh, sorry. Yeah, sorry. So the next session. By tomorrow, I mean the next session.
Yes. Okay.
Right. So great, everyone. If there is any doubt, you guys can ask here. I'll share the task as well as some references and so that you can be aware about some different things and try out some interesting stuffs by yourselves. All right, so if there is no doubt, then you guys can just leave. Or if there is any doubt, you can just be here and ask.
Thank you.
Yeah, thank you. I'll stop recording.